Okay.
Okay. All right, everybody. A very warm welcome to all of you. I was actually quite astonished to see the number of people who expressed interest in this lecture series. About 80 people. Of course, out of those 80 people, we'll see how many actually end up attending. I'll be happy if I have 20 consistent attendees. So we have a wide variety of people here, a very diverse range of people. We have MSc students, PhD students, postdocs, and some people are faculty also, but I don't think that any of the faculty have joined today. So first, just a few words about myself. My name is Deepak, and I am presently working as an assistant professor in physics at a small engineering college in India, on the west coast of India. My research, as you know, is on loop quantum gravity. I did my PhD from Penn State with Stefan Alexander and Martin Beaudevort. And so my interests are quite diverse. They from condensed matter to quantum information to deep learning, and somehow at the interface of all of these different ideas. So these lectures are meant to be pedagogical, and they are meant to be friendly. You can please feel free to ask a question at any point in time. You can unmute yourself and ask a question. And of course, in the event that I feel that a question is not so relevant, I might delay the answer until a later point. But please don't hesitate to ask any questions. And generally, I find that there is no such thing as a stupid question. Unfortunately, that we are told as students that don't ask stupid questions. But what I have found is that what we think are stupid questions are generally not stupid. In fact, everybody else is thinking the same question, but nobody is going to ask them. So generally, when a person asks such a question, it helps clarify something important for everybody. So, and I have, for this purpose of facilitating group discussions, I have set up a Google group mailing list, and I think all of you are on that. If you're not already on that, then mail, and I will add you. I have also set up something called Zulip Chat. And Zulip is a wonderful discussion software. It's completely open source, and it's fabulous. It has LaTeX support and also Markdown formatting. So that is very nice if you want to have scientific discussions. So, and these talks will also be recorded and live streamed on YouTube. So with that being said, I think I will start sharing. And okay, so loop quantum gravity. Now, a lot of people are interested in quantum gravity, right? And that is considered one of the unsolved mysteries of theoretical physics. So of course, everybody knows about string theory. Everybody's heard about string theory. String theory is as I say, the 400-pound gorilla on the block. And string theory is, I mean, loop quantum gravity is definitely, you know, as they say, David to string theory is Goliath. So of course, but the ultimate point is not that David is going to bring down Goliath. I don't see that as, you know, I don't see it as one versus the other. I think both are both provide very valuable insights, and the tools and methods used in both loop quantum gravity and string theory are going to ultimately be useful in constructing a complete, consistent theory of quantum gravity. So this is just you know, usual stuff, introduction and so on. So the first question that you know, one would ask is, why quantum gravity? I mean, why should we care at all about a quantum theory of gravity, right? So, well, we have, after all, we have the standard model, and the standard model of particle physics is very successful, right? It tells us that you can put all the quarks and leptons, and along with a certain number of gauge bosons, and all of that can be compiled into one big Lagrangian with about 16 different coupling constants, and that can be used to predict the properties of matter. But this is not exactly the most elegant picture. First of all, right? You have 16 coupling constants which you have to specify by hand, through measurements. And the most important thing is that the standard model does not include gravity, right? As such, it describes quantum field theory, free quantum fields interacting on a flat background, on a flat Minkowski background. So then you know, the natural thing is to try to formulate a theory of quantum fields on curve geometry, right? And so one can do that as long as the curvature is not too high. So there is a way to do that. But the problem is again that in regions where the curvature becomes dynamic, where the background becomes so to speak, you know, if you look at a system, it can have fast degrees of freedom and slow degrees of freedom, right? So generally, you know, if you have slow degrees of freedom, one can you know, make an approximation in which those are static, and then you know, one can solve for the fast degrees of freedom. So the idea would be that you treat the gravitational field as your slow degrees of freedom and the quantum fields as your fast degrees of freedom. But when your gravitational field becomes very strong, or it becomes you know, very dynamic, then the methods of quantum field theory on curved spacetime are no longer going to be successful. Then we have many unsolved mysteries, right? There's the question of neutrino masses. There is the hierarchy problem, which is the question that why is the mass of the electron, for instance, so much larger than the mass of a neutrino, and why is the mass of a proton so much larger than the mass of an electron? And why do neutrinos have masses at all? And why are neutrinos only left-handed? Why are there no right-handed neutrinos? Then we have this question about the Big Bang. So we have some idea of what, you know, happened in the initial stages, and there are very successful theories which give us predictions which have been verified to a large degree of accuracy. The cosmic microwave background and other and large-scale structure, for example, these are you know, predictions of inflationary theory, and they have been verified beautifully by satellites starting from starting initially from the initial observations of the cosmic microwave background by Penzias and Wilson back in sometime in the late 1960s, and then with the launch of COBE, Cosmic Background Explorer, in the beginning of the 90s, to W map, Wilkinson map, another satellite observatory, then followed by the Planck satellite, which is currently going through its observational runs. And so even though that the predictions of inflationary theory have been verified, there still remains the question of what inflation is as such. There's this picture of a scalar field rolling down a potential. It seems very ad hoc, right? I mean, where does the potential come from? What is the scalar field, right? We don't know. I mean, it's just a sort of a recipe which gives us a nice answer. So all of these questions, it doesn't seem that they can be resolved purely within the framework that we have had of quantum fields and the Standard Model. And most importantly, the reason for quantum gravity is, well, if you come up with new ways to think about nature, then that leads to not just to new philosophical understanding of nature, but also it yields tangible results in the form of technological developments, right? I mean, if you think about how much time passed between the discovery of, let's say, electromagnetism or electromagnetic theory and the synthesis by Maxwell of his 4 equations, right? So at that point in time, very few people would have believed that just 30 years from that Maxwell's publication of his 4 equations, that this concept of electricity would have become common, and people would no longer have to live in the dark, right? I mean it was literally the dawning of a bright age, which happened very rapidly. So we should not underestimate the potential for new theoretical discoveries to lead to new technologies on very short, on the time scales of less than our lifespan. Now there are there have been many attempts to construct theories of quantum gravity. So now one can start with the Einstein-Hilbert action, and then one can construct a field theory in different ways. One can go, there's a covariant way, there's a canonical way, and but ultimately what happens is you run into difficulties which arise from the so-called non-renormalizability of the Einstein-Hilbert action. And this can be traced back in part to the fact that the coupling constant for Einstein gravity is a dimensionless, is a dimensionful constant, and it has units of momentum squared. Whereas, for example, if you look at QED, the coupling constant is the fine structure constant, and it is dimensionless. So essentially what this says is that if you, for instance, write down the Feynman diagrams for the scattering of gravitons, then you might be able to write down the tree level amplitudes, but then if you try to calculate loop amplitudes, you will find divergences, and those cannot be removed by any kind of renormalization of the coupling constant or of the fields. So then the possible way out is that maybe, well, the Einstein-Hilbert action can be modified by adding, let's say, terms of which involve higher powers of the curvature or higher derivative terms. But what happens is that if you do that, well, you can make the theory renormalizable, but that comes at the expense of destroying unitarity. right? So the resulting quantum theory has states of which have negative norms, and so that is not good, right? If you want to have a theory which gives you physical predictions. And then, of course, we have string theory. Now, string theory is indeed a beautiful theory, but what happens is that you start with the concept of a string moving in a flat space-time, and you write down the associated quantum theory, and then you quantize it, and you apply this background Poincare invariance of the string, which leads you to a certain value for the critical dimension that the string must be moving in. But then that turns out to be 26. Now, obviously, that is a sort of a weird thing to say that space-time is 26 dimensional, because, well, it doesn't appear to be. Right? So then the notion is that, well, maybe it's because we didn't include fermions in the theory. So you introduce fermions, then you have supersymmetry. And then in the theory with fermions, the superstring can be formulated in 10 or 11 dimensions. Again, that's not exactly, 4 dimensions. So then the suggestion is, well, what happens is that 6 or 7 of those dimensions, they curl up, they compactify into, they become very small, and they are not observable, and we are left with 4 large dimensions. The problem with this is that there are sort of an unimaginably large number of ways in which you can compactify these dimensions. There's like 10 to the 500 ways, or some number of that order. And the problem is that we don't know which one of those compactifications will lead to something resembling our Stein's model. Right? So clearly there is, so then people are thinking, well, maybe, one has to apply machine learning to this vacua, and so on and so forth. But maybe there is something wrong with one of the starting assumptions, right? Somewhere along the line, the string theory in the progression from the introduction of the quantum theory of the string to the derivation of the critical dimension, maybe there has been some mistake somewhere. And the mistake that that some of us, those in the loop quantum gravity community, feel is that the string theory makes, first of all, it makes the assumption of a smooth space-time on all scales, right? That is an implicit assumption of string theory. The second assumption is that string theory, is formulated on a flat space-time, right? And the dynamics of the space-time is not included to begin with, right? So one goes on to say that, well, from the effective string action, one can obtain the Einstein-Hilbert action and so on by looking at the beta function. But again, the point is that it's not clear in what sense is, so the string seems to exist independent of space-time, independent of geometry. And somehow there is this notion, this intuition that we have that, well, geometry itself should have a quantum character, right? And if we say that, well, strings are fundamental objects, then one should be able to describe, for instance, one should have a description of strings which does not depend on a space-time. One should have a background independent description of strings. So we don't have that yet, right? And maybe the hope is that perhaps loop quantum gravity provides a way to give such a description. And many people, such as Lee Smolin, Fotini Markopoulou, and myself, we have argued that, well, string theory and loop quantum gravity really are not that different. And other people also who have done very good work, Jorge Pulin and Rodolfo Gambini. So, and now, of course, it's becoming gradually less and less controversial to say that loop quantum gravity and string theory are not incompatible. And I think pretty soon in the coming days, months, and years, you'll see it'll be quite remarkable how quickly it goes from being a taboo subject to being the most obvious thing to say that, oh, well, of course, string theory and loop quantum gravity are the same. How can they be different? And then the rest of us, we will really look at that and think back to the times when that was not the case. So let me give you a brief. So are there any questions at this point? And of course, the audience consists of a lot of experienced researchers. So many of you might have you might notice that I might say something that you think is incorrect, or you might want to provide some inputs. So I urge you to please chime in at any point. I just want to say that I'm very much a student, and every day I'm learning, and my ignorance becomes more and more apparent to me as time goes on. So yeah. So please correct me if I say something wrong at any point in time. Okay. So the beginnings of LQG can be traced back to well, they can be traced back to the Big Bang, but in terms of the theoretical development, a physicist called Amitabh Sen in 1981, he introduced something called the spin connection into general relativity because he was looking at neutrino zero modes. So zero modes are basically so neutrinos are fermions, right? And so to describe fermions, you use the Dirac equation. And so the zero modes are the massless modes for which the Dirac operator acting on a fermion is zero. And but the problem is that if you want to study the solutions of the Dirac equations in a curved background, then you can't do it using the normal Einstein-Hilbert action, because the Einstein-Hilbert action in terms of the metric and the Christoffel connection, it doesn't know anything about fermions. So we will talk about these things later. So the solution is that, well, you introduce a spin connection, you introduce a connection which does know about fermions. And then in 87 and 88, Abhay Ashtikar, who introduced in his monumental paper, the new variables for classical and quantum gravity. So what he did was he took the old variables, which were the Christoffel connection and the metric, and showed that you can rewrite the Einstein equations in terms of something that is called the Ashtikar connection for obvious reasons, and a tetrad. So we will see later what a tetrad is, what this Ashtikar connection is. But the point is that he showed that the phase space of general relativity, for example, the kinematic phase space is exactly the same as that of Yang-Mills, right? And this was a revolutionary discovery because Yang-Mills is a gauge theory, and people knew how to quantize Yang-Mills. We had quantum chromodynamics, which was a theory of the strong force, and so immediately the windows opened and the sun shone in, and because people suddenly realized, well, we can apply all those techniques now to quantize general relativity, right, which has not been amenable to other methods of covariant and canonical quantization. Then so the discoveries came quite rapidly. Carlo Rovelli and Lee Smolin, along with John Baez and others, they realized that the solutions of general relativity can be written in terms of something called a spin network basis, and that in this basis you can define certain operators which measure the areas and volumes of a given region of space-time. And so this was a remarkable development, which um, went underappreciated, frankly speaking. A part of the reason was because at the same time, well, like I said, string theory had been developing for much longer, right? String theory started in the late 60s. So it had the early mover advantage. And then there was, so at the beginning in the late 70s and early 80s, when people realized that the string spectrum also contains a graviton, so that is when string theory started to become a candidate for a theory of everything, right? And but there were certain anomalies in string theory. But then in mid 80s, there was something called the first string revolution, where they showed that you can use that those anomalies can be cancelled out in the superstring. And but then there were again other issues that popped up, and then there was the second string revolution, which happened around the same time as this quantum geometry was being explored. And so that received a far more public and also research exposure. And the world was gaga with the possibilities that string theory presented, right? I mean, it was the theory of everything. It would describe everything starting from nothing. And that did kind of overshadow any other competitors. But of course, there was that seed of doubt that existed, right? Which I believe is what has grown and until it has become loop quantum gravity. That seed of doubt is this notion of quantum geometry, which was not present in string theory and is still not there. Then following up on these developments, you had work by Ashtaker, Rovelli, Corici, Alejandro Corici, Kirill Krasnov, John Baez, and others, who showed that in the first application of this new framework, they showed that you can use this to count the microstates of a black hole horizon. And so we have the very famous Bekenstein-Hawking formula, right, which tells us that the entropy of a black hole is proportional to its area. And then we have the results of Hawking and Carter and others, which show that the horizon is a hot object. It's a thermal object. It emits radiation. So that means it must have some microstructure, right? Well, the fact that it has an entropy means that it has to have a microstructure. But then that is at odds with the fact that with the so-called no-head theorems, right? So we say that when the process of gravitational collapse completes or reaches its conclusion, you are left with an object which can be described purely by mass, charge, and angular momentum. And so there really is no room for any other states. But then the point is that, well, that you should think of a black hole as a thermodynamic system or the many-body system, and mass, charge, and angular momentum then become the thermodynamic parameters which describe a particular state of this system, right? In the same way that if you look at a gas, for instance, you say that it has a certain pressure, a volume, and a temperature, and so on, and that describes the macroscopic state of the system, right? So in the same way, there is a certain microscopic description, and that can be described by this quantum geometry. Of course, at the same time, around the same time, Juan Maldacena did his amazing work showing that this correspondence between anti-de Sitter spacetime and certain conformal field theories, which has been verified over and over again in many circumstances, and now stands as one of the pillars of high energy physics and theoretical physics. So ultimately, that holographic conjecture or holography, I mean, it's not really a conjecture in my opinion, but nobody's given a proof as such. That holography will be where loop quantum gravity and string theory meet. So at that time, following Malsena's work, Strominger and Waffa and others, they showed that you can do the same calculation for black holes, starting with certain states in string theory called BPS states, and counting those states gives you the Beck-Stein-Hawking formula. But there was a crucial caveat in the string theory calculation, which is that it applied to extremal black holes. And so, I mean, if you think about extremal black holes, are those, which, so you can have rotating black holes, and black holes can have charge. So there are certain limits that are placed on how fast a black hole can rotate or how much charge it can have, right? And when a black hole saturates those limits, it's called an extremal black hole. So now there might well be extremal black holes in the universe, but the point is that I mean, until you can give a description for non-extremal black holes, it's more of a theoretical achievement than anything else. Whereas the loop quantum gravity counting, for instance, applies to black holes or a short-shell black hole. But that is also not satisfactory, right? Because black holes in nature, they might not be extremal, but they are also not necessarily short-shelled. I mean, short-shelled is, in fact, black holes are not described by a short-shell metric, right? They almost inevitably have some rotation and most likely have some charge also. So ultimately, the challenge is to do this microscopic counting of states for black holes with rotation and charge. And that's something that has not been done in loop quantum gravity yet. But I think that it's about to be done. So these are some of the beginnings of. Yeah.
Can I ask a question?
Yes, of course.
Sorry, can you hear me?
Yes, I can hear you.
What about the information paradox? What is the loop quantum gravity? Is there a solution from loop quantum gravity or not?
Right. So,
as you know, string theory now.
Absolutely, yeah.
The Iceland conjecture. So yeah.
Right. So the information paradox. Well, my understanding of it is also very incomplete. Somebody raised their hand. You really don't need to raise your hand unless there are many questions. So you can just ask a question right after I answer Alessandro.
Yeah, sorry, I have to raise my hand. So
no, it's okay. It's okay.
Sorry.
We only have 18 people, 18 participants. There's really no need for anybody to raise hands or anything. I mean.
Thank you.
So this information paradox is one way to state is that from what we understand it, a black hole, according to Hawking's description, it emits radiation and its mass shrinks, and then eventually it disappears, right? The space-time doesn't have a black hole after some time, and we are left with a bath of thermal radiation. So the question is that, well, you have thrown a lot of information, like you have thrown, let's say, correlated systems, you have thrown entangled objects, you have thrown, computers, you have thrown elephants or people into the black hole. way of thinking about it. You don't actually want to do that, obviously. But the point is that all of these systems, and then afterwards you're left with a purely thermal path of radiation, right? Where there are no correlations between the photons of that bath. And so if you think in terms of if you think in terms of the evolution of a quantum field, you start out by defining a quantum field on an initial called Cauchy surface, right? And initial on the space time, and then you evolve it through as the black hole forms and then it starts to decay. What you find is that quantum field is not, you don't have a unitary description of that evolution. So that is often what is known as the information paradox. Like where has all that information gone, right? How do unitary systems fall into a black hole and somehow become non? How does their where do all the quantum correlations vanish? And so the idea is that, well, if you have a complete theory of quantum gravity, then one should be able to treat space-time as a quantum state which evolves, and so there should be no loss of information. Whatever information is there in the quantum state of the space-time initially should be the same as it, and it should be the same later on also. So the question as to whether loop quantum gravity provides a resolution to this, and the answer is no. I'll be honest. There are, but I mean, I believe that loop quantum gravity contains all the tools that are needed to provide the resolution for it. So, but again, that is something that we will discuss in more detail, I think, later on when we talk about the degrees of freedom of the black hole horizon, for instance, and how they can interact with each other. So, again, I don't know if that sufficiently answers your question. And the resolution, there is a resolution which is like, in terms of ADS CFT. So one could say that provides a resolution of this information paradox, because the bulk geometry of anti-de Sitter space-time is described by is mapped into the quantum field theory living on the boundary. And so you have a completely unitary description of the bulk geometry in terms of this quantum theory, this conformal field theory. Technically speaking, your geometry does have a unitary description and there is no information loss. But again, there are many issues to be hammered out in that picture. That is one reason why I believe that ADS-CFT is very crucial to understanding the information paradox in loop quantum gravity also. Then we have a question from others. I think Debamalya has a question.
Yes, sir. My question is, you have mentioned about no-here theorem. Can you hear?
Yeah, I can hear you.
The thing is, and you have talked about the entropy of black hole. The question is, since the entropy is an extensive quantity in thermodynamics, so how is it compatible with the no-here theorem, which tells only 3 parameters are needed to describe a black hole? But now,
yeah. So I mean, there's no. I mean, it's like talking about a gas in classical thermodynamics, right? I mean, you have pressure, volume, and temperature. So of those, let's say the volume and the total energy, for instance, are extensive parameters, right?
Yes, sir.
And you also have an entropy for that gas. So there is no conflict with the extensivity property and the entropic property, right?
The Noether theorem was made for the temperature zero case.
Well, I mean, the zero case is the extremal black hole, I believe. So yeah, I mean, the Noether theorem, I think it should apply to, it applies to gravitational collapse in general, right? I mean, because it is based on certain singularity theorem. But again, what's the point? What's the question? That is what I'm trying to understand.
Should I assume that entropy is a function of the other extrinsic quantities, like?
Yes, of course. Entropy is a function of the extensive quantities, right? It's a function of the mass. It's a function of the area.
Noether theorem.
These are all extensive quantities, right?
That is why I am asking. And one thing is, does LQG provide the proof of Noether theorem? Or it has...
No, I mean, of course, the point is that there are hairs, right? I mean, the no-hair theorem is something that is based on an understanding of geometry which doesn't take into account quantum gravity.
Okay.
Right.
Okay. So I've
but
been
ultimately the point is that
theorem. That's why I've been informed that there is no any proof, solid proof of Noether theorem. I do not know whether it is right.
Well, I mean, again, I don't want to comment on that. I honestly have not delved into the Noether theorem in great detail.
Okay.
So I can't really say, but I mean, it's a theorem, so I presume that it has a mathematical statement and a corresponding proof. But it is, again, there is a certain setting for any theorem, right? And that setting may include certain assumptions, which may not, if once those assumptions are violated, the theorem no longer holds true. Right?
Okay.
So, and I think there was some, Juan had maybe a question, or somebody else had a question?
No, it is okay.
Okay. All right. So with this introduction of beginnings of LQG, so just wanted to flash a picture of the big three, Ashtikar, Smoley, and Rovelli. And of course, there are many others who have also made contributions to the development of LQG. And there's a very long list of people, and I will run out of slides if I try to include all the people. So, but some of them include, for instance, Joseph Samuel and Ted Jacobson. Ted Jacobson is famous for his 1995 paper, right, which showed the connection between thermodynamics and the Einstein equation. But it's not so well known that he is also intimately associated with the beginnings of loop quantum gravity. Then there is Hideo Kodama, who developed something known as the Kodama state, which is an exact solution of the Hamiltonian constraint, and it corresponds to the de Sitter universe. Then we have Fernando Barbero and Giorgio Imizzi, who discovered that there are certain ambiguities in the formulation of loop quantum gravity, which lead to the introduction of something which is known as the Barbero-Imizzi parameter, which there is still a long-standing continuous debate as to whether or not the Imizzi parameter has any physical significance, and if so, what is its significance? Then there are other people, Barbieri, who talked about the properties of a quantum tetrahedron, which we'll talk about at one point, which is like a basic atom of geometry. And then Krasnov, who also contributed to the black hole entropy calculation. Then we have Barrett and Crane, who came up with the model that goes by their name, the Barrett-Crane model, which is a discretization of four-dimensional general relativity, and which leads to something called a spin form. So we will also discuss that at a later point. And The spin foam concept itself was first introduced by Reisenberger in a paper with Rovelli. And John Baez has been throughout involved in work with many of these other people. Then Fotini Marco Polo has done a lot of work on, for example, investigating the existence of string-like physics in loop quantum gravity. And then, of course, Martin Bojo-Wald is he's considered a giant. So perhaps there should be a second box here for Martin Bojo-Wald, a fourth box, because he's the person who has discovered loop quantum cosmology. Then there is Thomas Thiemann, who's a little less well known, but because his contributions are mostly mathematical, but they are very, very foundational. They're very important to the foundations of loop quantum gravity. So then we have Rodolfo Ciampini and Jorge Pullen, who have also done a lot of work. Again, I can't, if I start mentioning everything everybody has done, I think all of you will fall asleep. Though the work is exciting, right? Then Reggie is famous for the calculus which goes by his name, Reggie calculus, but he's also contributed later on to developments in loop quantum gravity. Dreyer. Then this is Uric. His name is pronounced as Uric. That's from what I've been able to gain from meeting people. Uric Lewandowski. He has also done foundational work along with Hanno Salman. Then Jonathan Engel is a very important researcher. He was my senior in graduate school, and he was a Abhay student. And he is one of the people behind what is known as the EPRL vortex, which has become very famous in the past 10 years. Then Renate and Jan, they are the people who have developed causal dynamical triangulations, which is another sort of a loop quantum gravity-like approach, but not the same in all aspects. Then Leonardo Modesto. Then Sundance Wilson Thompson, a longtime collaborator and friend of mine, who introduced the idea of topological particle states in loop quantum gravity, which became a big deal for a short amount of time, but then they died away as a fad, and then over time people have forgotten about it. But I believe that his work still stands and will be vindicated. I think sooner rather than later. And then we have people like Etra Levine, Laurent Freudel, Alejandro Perez, who are very active researchers, and these are the new leaders of the field at present. And then Andy Randono, I think he left theoretical physics, but he did a lot of important work in the Kodama state. And Stefan Alexander, one of my co-advisors, Simone Speziale, and then Ivan Agulo, Alejandro Corici, and a lot of other names. There is a whole bunch of new generation of researchers whose names I have not mentioned here. So this is the background for loop quantum gravity, and the motivation for loop quantum gravity. So I'll pause here for any other questions or any other or any if you want to take a break maybe. No? Sure, I'll continue then. Okay. So, well, this is where it all begins, right? Einstein's field equations, the general theory of relativity. So you have this G, right, which is the Einstein tensor, and on the left-hand side, and on the right-hand side you have this T, which is the stress energy tensor. So this tells us what the matter is doing, right? So Einstein tensor is a geometric object, and it is related to the Ricci tensor. It's the trace-free part of the Ricci tensor. sorry, it's the divergence-free part of the Ricci tensor. And so this is a purely geometric quantity, and this T is this describes the matter field. So as you all are familiar with these pictorial descriptions, that when you have matter in some region of geometry, the presence of matter causes curvature, right? And for instance, and then if you have other objects, smaller objects, then those objects follow geodesics in that curved space. And that geodesic is what we observe to be, for example, as orbital motion. So in a sense, particles or objects, planetary objects or bodies are always following. They are moving free. They are falling freely through space-time, right? Of course, this whole picture of geodesic motion and point particles is restricted to the node. It's okay as long as you have point particles, but we don't really have anything in nature such as point particles. And the moment you start talking about extended bodies, these notions all become a lot more approximate. So there's a whole very active body of work that has been done by many people. One of them is a good friend of mine called Abraham Harte, one of the most talented physicists in the world, I believe. So this is for those of you who are into mathematical physics and such things. Sorry, the motion of extended bodies in general relativity. Right, so here's a pretty picture of black holes, and it's taken from Interstellar, which of course does no justice to the actual physics of a black hole. But it's a Hollywood movie. So I guess we don't need to go over all this history of quantum mechanics, as most of you are familiar with this, right? So, but let me talk a little bit about the structure of quantum mechanics. Right, so we in quantum mechanics we say that, well, you have any physical system, right? It doesn't matter how big or how small, is described by a state vector, right? Or you can of course use the density matrix formulation if you so wish, in some vector space, which is which is a Hilbert space. And then one has dynamics and observables are given by the action of operators, right, which takes states from one state to another state. So for instance, one can write down a Hamiltonian for n objects, right? So this is just the sum of the kinetic energies and the momenta for n particles. And corresponding, one can quantize this by replacing the momentum operator, by replacing momenta by the operators, and then hopefully solving for the eigenstates of the Hamiltonian, if that is possible to do. And then we have, finally the notion of superposition, for instance, that if you take any two or more states, then you can construct a linear superposition, and that is also a state, right? So you can have something like a particle which is in two places at the same time. But there are, many issues with quantum mechanics. So, for example, there is the so-called measurement problem. Again, these are not really problems according to many physicists. So many researchers would argue, well, there's not really any measurement problem. You just have to think about the many worlds interpretation, and there is no question, no collapse. There's no such thing as collapse. But if you are skeptical about many worlds as I am, and then if you think that, well, it's not clear how the wave function of the universe could keep branching at each point, because I just think like a computer scientist. I was when I was growing up, I was very very much into programming, and so that has influenced my thinking a lot. So whenever I think of this idea of the wave function branching, I think about, well, how much information would it take to keep track of all these branches, and where does that information go, right? And quickly that one can see that, well, that hypothetically or theoretically it might sound like a reasonable idea, but very quickly it becomes unfeasible if you think about it in terms of computation and computational resources. So and well, ultimately, if you cannot keep track of that computation, then you can't really do physics. So the question is that, well, this whole idea of a measurement, this whole idea of a collapse, can we give a more complete picture, a more better description of it than what we have in terms of the Copenhagen interpretation? That is a challenge. Then we have the question of background dependence, right? So quantum states are implicitly and explicitly also defined as, for instance, functions of momenta, or you can of course define them as functions of position also. Or one can have a quantum state of a spin. Now you might say, well, the quantum state of an electron with spin 1/2, it doesn't have any dependence on position. But if you want to talk about, let's say, the interaction of that electron with other systems, then you have to introduce a position and a time coordinate, right? So quantum states are inevitably, they are functions on space-time, and so they have the dependence on a scaffold, right? This scaffold is a space-time background. But so what happens if that scaffold itself is dynamic, right? What happens if your x and t are no longer something that you can define in an invariant manner? Then in what sense will you define these quantum states? So there also one can construct a proper quantum theory, actually. So this is not something that is an insurmountable challenge. There is what is known as the boundary state description of quantum mechanics, where you look at some region of space-time and you look at the state of the system on the boundary, and so this is associated with so I don't remember the exact word for it, but something like the boundary formulation.
Excuse me, Deepak.
Yeah.
I have a question. Could you elaborate a bit more on the second sentence under background dependence, that in a dynamic curved spacetime, it is not clear how to define positions and momenta in an invariant manner. Could you elaborate on what you mean by invariant manner?
Well, invariant manner means so yeah, okay. Well, let's say that you have some. So okay, so let me. This is why I have. Okay, so let's see. So let's say that you define some state. So you have some state, and let's say I write it like this, right? Now this gives me and then if I associate a state with a given, this is the spatial slice at a given time, right? And let's say R3. Okay. Now the thing is that if you talk about if you talk about curved space-time, right? So in curved space-time, for instance, well, what would you do? Well, you would say, okay, fine, I just have to introduce, let's say, a determinant, square root of the determinant, right? Isn't that enough to make everything work out? And this itself is not sufficient, because okay, yeah. So let me see how I would answer your question.
Deepak, we can talk about this later if you want. If you want to continue with the lecture, then that's fine.
Sure, I would appreciate that.
Yep, sure. Thank you.
Okay. Okay, so all right. So then the challenge becomes that if we start with some abstract set of quantum states defined without respect to a background scaffold. So if you want to talk about how quantum gravity might emerge simply from quantum mechanics, then the question becomes, well, how do you generate the scaffold starting from a set of quantum states? How do you do quantum mechanics in the absence of space and time? Okay. So, okay, anyways, I've already gone through all of this. And all of this also. Okay, all of this also. And then there is this beautiful graph that is that I've taken from an old paper, well, 2006, 14 years old, by Carlo. And it shows a very nice the evolution of the ideas of quantum gravity, right? So it starts from 1920 and then continues on up till around 1997, right? So it's quite a beautiful summary. So I think that, well, justice would be done if one extends it beyond 1997 to the present day. But this gives you a very nice bird's eye view of the development of quantum gravity, right? And the branching off of quantum gravity into many different lines of research, right? So you have the recognition in the early 1920s itself that the gravitational field would need to be quantized, right? And then the question is, well, how do you perform that quantization? So then you have one line of approach that you have one line of approach that looks at systems with constraints and how to quantize systems with constraints. And because it becomes apparent that, for instance, if you look at the Hamiltonian for general relativity, it's a constraint. And so that leads to the ADM formulation and the wave function of a 3 geometry, leading ultimately to the Wheeler-DeWitt equation, which at one point was thought to be to provide the solution to a problem of quantum gravity. But then later quickly people realized that, well, except for some very special cases like isotropic spacetimes, one can't really solve it. So it doesn't tell us all that much. And then you have the covariant approach, which basically works by writing down the partition function for all geometries, which would look like something like you have an integral over the space of all metrics, and then you have some exponential of the Einstein-Hilbert action, something like this, right? So basically, the functional approach to quantization. So this also, and then you have the notion of treating. You start with the Einstein equation, you linearize the Einstein equation, right? And then you get a differential equation for fluctuations around some given fixed background. And then you say that, okay, I can treat that background as a classical object, and you try to quantize the fluctuations around that, right? So that's this flat space quantization. Then you can write down Feynman rules for the interactions of gravitons and so on. And then you can see that, this functional approach eventually evolved into the Euclidean quantum gravity approach of Hawking and Page, for example, and led to something, this wave function of the universe idea, and this thing, the flat space quantization approach, that led to problems which arise because of there is some gauge dependence, right? You have this diffeomorphism invariance. So how do you implement that diffeomorphism invariance? You have to introduce it as some sort of a constraint. And the way you do that is by introducing ghosts. But if you have ghosts, then again, your theory develops all kinds of problems. So you have a renormalizable theory of Yang-Mills, but the Einstein theory is non-renormalizable. And so people think of, around 1970s and so on, for instance, this notion of asymptotic safety is discovered by de Hoogt, right? Which says that if you look at Yang-Mills theory at strong coupling, it becomes asymptotically, there is this notion of asymptotic freedom, right? That it becomes a non-interacting theory and exactly solvable. So there's a similar kind of hope for gravity that if you look at sufficiently high energies, there is something called a non-trivial ultraviolet fixed point, and that if one can find it, one can define gravity consistently, quantum gravity consistently at arbitrarily high energies. Then, of course, you have this supergravity and higher derivative theories, which again have their own individual merits and demerits. And then this was the 70s and early 80s. And then the canonical or the phase space approach that went through a long period of stasis until the late 1980s with the discovery of the connection formulation, and then loop quantum gravity, and then things quickly blew up. And the flat space quantization approach, that eventually merged with what was string theory, and you had superstrings. And then around the mid 80s, due to work by Witten and others, topological quantum field theory was discovered, right? Following the discovery of the Jones polynomial, for instance. And but then there was a very interesting convergence in the mid 90s, where people realized that the states of loop quantum gravity, they can be given a description in terms of a topological quantum theory, and that led to this spin forms. So of course, since 1997 till now, we have had a whole lot more. We have had massive amount of development, right? We have had holography. So this pretty much ends at holography, right? And so we have a whole different branches. So, but again, I don't want to go into the whole history of quantum gravity. Maybe we might take some time out at some point to talk about these different approaches. But the goal of these lectures is to enable you to understand the technical tools of loop quantum gravity. Okay. Anyways, so the starting point is the Einstein-Hilbert action. Okay, so this is where the quantum gravity begins. So what is the Einstein-Hilbert action? Well, it's this object. You have your Newton's constant. You have R, which is the Ricci scalar, lambda, which is the cosmological constant, and Lm is the Lagrangian of whatever matter fields might be present in this background. Right. So now you can perform a variational, usual variational calculation, and this calculation yields the Einstein equation, right? So you obtain the Einstein field equation as an extremum of this given action. So this action then becomes the starting point rather than the given extremum itself, because as we know from our understanding of path integrals in quantum mechanics, the saddle point or the extremum of the action that only coincides to the classical description, the classical theory. But to describe quantum states, one has to look at all possible trajectories with different possible values of the action. Right? So, in order to be able to do that, right, one can't just throw away the action, right? One has to work with the at the level of the action principle itself, right? So how do you do that? Well, there are two ways. One is that you can go and talk about, let's say, a Hamiltonian, or you can look at the action as it is and think of it as a Lagrangian, and then you kind of try and apply the tools of functional quantization. So in either one of those two cases, one has to first understand how to write down the Einstein equation or the Einstein-Hilbert action in the Lagrangian form or the Hamiltonian form, right? So anyway, this is all just formalism. So if we want to write down, and since loop quantum gravity comes from the Hamiltonian approach, that is what we'll begin with. So this Hamiltonian or the ADM formulation, right? This starts off from an assumption that you have some four-dimensional space-time, and you can foliate that space-time, right? So this is some four-dimensional space-time. This is the time direction, and these surfaces normally they're labeled, let's say, sigma t, like this. This is a surface of constant time, and so this is a spatial surface, and this is the surface at another point in time, let's say sigma t prime. And then you can define a certain vector field, which is this time evolution vector field. And since we are in a curved background in general, the time evolution need not be the time evolution vector field need not be orthogonal to your spatial hypersurfaces, right? Because your spatial hypersurfaces, for one, they can have extrinsic curvature, right? They do not need. So this time evolution vector field can be decomposed into two parts naturally, because if you take any vector, right, you can decompose it into the sum of two other vectors which are orthogonal to each other. So in this case, what are the two natural orthogonal vectors? Well, one vector is the one which is orthogonal to a hypersurface. So you have a hypersurface, right? So just like I have a sheet of paper or this surface here, and this is the orthogonal vector field. And then there is a space of tangential vector fields, all the vector fields which live in the tangent space at that point, right? So I can take any vector field and decompose it into an orthogonal field and a tangential field. And that's essentially what is happening here. This is the orthogonal piece, and this is the tangential piece. So this is, and here, so n is something which is called the lapse, and it's a function in general of space-time, and NA is what is known as a shift vector field. So now, in terms of these shift and lapse vector fields, one can define various other quantities. So one of the important quantities is what is known as the metric of that hypersurface. So you have the metric of the full space-time manifold, right? You have G mu nu, and if you take G mu nu, so actually these slides are actually a little bit older. So let me insert another page. So you have your full 4-dimensional metric, right? And what you want to do is you want to describe it. And in terms of this, you have a 4-dimensional metric, and then you have some Christoffel symbols, and from this Christoffel symbols and metric, you get your Riemann and Ricci tensors, right? But this metric exists independently of the way in which you foliate your spacetime. So if you think about what happens in Hamiltonian mechanics, right? In Hamiltonian mechanics, what you have positions and you have momenta, coordinates and generalized momenta, right? And so the question is that if you talk about gravity, right, or general relativity or geometry, then the question is what should be the coordinates and what should be the generalized momenta of the gravitational field, right? So what is the configuration space of the gravitational field? So one natural candidate for this configuration space is that if you consider the spatial manifolds, right? Sorry for that. These spatial manifolds will have some intrinsic metric. Let me write that as HAB. Okay. So here notation is that if you have these mu, nu, alpha, beta, these are 4-dimensional space-time indices which take values from 0 to 3. And if you have lower case indices such as A, B, C, D, these are spatial indices which take values from 1 to 3. And then later on, we will also use indices which are, oops, sorry about that. We will use this indices capital I, J, K, L. So from the middle of the alphabet. And these we will see go from 0 to 3. And these will be Lorentz indices, Lorentz or SL2C indices. And this small I, J, K, L will be SU2 or SO3 indices. And so these are 4, if you talk about the Euclidean picture, or R31 indices, and these are R3 indices. Okay, so this is our notational, these are our notational conventions. So now when we talk about the 3 manifold, then we would write tensors on the 3 manifold or in any vectors or tensors using the lowercase ABCD indices, right? So for instance, the 3 metric would be written as HAB, right? Whereas the full 4-dimensional metric is G mu nu. Okay. But the important thing to remember is that HAB is something that is defined on, it is defined on sigma, right? But one can also write it as a full 4-dimensional tensor, right? So you can always take a lower rank tensor and write it as a higher rank tensor, right? By adding some extra rows and columns. So, so for instance, if you have this 3 by 3 matrix, right? Let's say it has components H, XX, XY, XZ, and so on, right? And you want to write it as a you can write it as a 4 by 4 matrix by simply saying that these components HTT and HTX, HTY, by setting these components to 0. Okay. Of course, that is requires a certain choice of reference frame, but you can always make such a choice. Right? And then the 3 by 3 component here, this would be non-zero. This would be your HAB. Okay. So this is an important point to keep in mind. So then we can define this quantity, which is H mu nu, and I can write it as this G mu nu plus this. What is this n? N is the normal vector to my hypersurface. So this is my hypersurface. N is a unit vector which is normal to my hypersurface. So n is a time-like vector. So if I take the norm of the vector, I get -1. Okay. So what happens if I take H mu nu and contract it with N mu? Well, you take the definition of H mu nu in terms of G mu nu and contract that with N mu. So the first term will just lower the index, will just give you N mu, and the second term will give you N mu, N mu, N mu. Now the fact that N is a time-like vector, time-like unit vector, means that when you take this contraction, you get -1. So you get N nu minus N nu, which is 0. So what this shows you is that if you take this tensor H mu nu and contract it with any vector which is perpendicular to your hypersurface, then the answer is 0, right? So that immediately tells you that this vector, this tensor, has to be a purely spatial object. It lives only in that manifold, right, to which this vector is orthogonal. So you can just think about this in ordinary Euclidean space. This is not such a mysterious concept. You consider, for instance, that you have some plane in R3, okay, and you have some normal vector here to your plane, right? And then you have some tensor, let's say TAB, and what we have is that TAB dotted with N AB is 0, right? So this means that the action of TAB on any vector, now if I take any vector V, any vector V can be written as a sum of a component orthogonal to the plane and a component tangential to the plane, right? It can be written as V parallel plus V perpendicular. And the action of TAB on this VA will always give me a zero when I act on the perpendicular component, and a non-zero only when I act on the parallel component, right? So in other words, right, that is what it means for this tensor to be defined purely in this plane. It is restricted to this plane. So if you work in a set of coordinates which is adapted to this plane, right? In other words, if I work in a set of coordinates in which my normal vector is one axis, let's say, and my other two axes are, let's say, x and y, and these two x and y, they span the plane, right? They're tangential to the plane. And then I ask, what is the matrix TAB, right? What will I get? I will find that TXX, TXY, TYX, TYY, these are the only non-zero components, and all the other components are zero. It's exactly the same thing for this spatial metric, right? So if you work in a set of coordinates which are adapted to this foliation, then we will find that in that coordinate, this tensor h mu nu, right, has non-zero components only for the 3x3 spatial part. Anyways, I'll stop here because I think a lot of people are, well, I thought people were leaving. I didn't know whether they are or not. So I think I'll stop here because I think we have had a lot of discussion for the day. Well, or maybe I can continue just a little bit more. Okay. Shall I continue just a little bit more? Okay. It seems like not such a good stopping point. So this is one of the conceptual points that sometimes people stumble over when they first learn this ADM decomposition. It was something that I stumbled over, because it's like, if you have a 4x4 object, how can I do? If I have a 3x3 object, how can I define it as a 4x4 object? And I say, yeah, well, this is how you understand it. So in this case, if you have a coordinate system which is not adapted to this plane, then what will happen? These components, these components of the tensor, they will also be non-zero, right? You can see that, right? But the action of this tensor on orthogonal vectors will still be zero, because the tensor itself, right, is a coordinate independent object. The tensor doesn't depend on your choice of coordinates. Okay. So we define this object h mu nu, right? And what we find is that this is something which is a purely spatial object restricted to sigma. And this we can identify with the metric, the 3 metric on sigma, right? Now, when you talk about geometry, right? Well, what is geometry? Geometry is measured in terms of metrics, right? At least, the traditional way to understand it. If you have a metric, it allows you to measure distances, you can measure areas, volumes, everything. So one natural candidate for this thing, for the configuration space of geometry, is that you look at this metric field h mu nu, or HAB, since we want to talk about, this is a 3 metric. So you talk about the metric of the entire spatial manifold, right? So this HAB is a field which lives on this spatial manifold, right? And this is our configuration variable. This is like so if you talk about a position, if you talk about a Hamiltonian of a particle, which has a position and a momentum, then this is like the position, right? This is like the initial configuration. Why? Because what happens later on, as time goes on, right? As time goes on, your foliation evolves, right? And when you are at a different time, your metric on the slices changes to something else, right? So with time evolution, right, HAB changes from one foliation to another, and this change in HAB, right, encodes the dynamics of your geometry. So then what should be the momentum variable? Well, again, we look back to classical mechanics for inspiration. In classical mechanics, what is our momentum? Our momentum is normally identified as something which measures the rate of change of your configuration, right? So here the momentum should be something which looks sort of like the time derivative of your 3 metric. Something which tells you how is this 3 metric changing in time, right? And we will see later that it turns out that, well, you need to define something called a Lie derivative, because it's not, you can't just take an ordinary partial derivative. You have to take you have to do something which is parallel transport, and so you have to define the Lie derivative of this metric, this tensor HAB, and this is equal to KAB, another tensor. This tensor turns out to be equal to the symmetric part of the covariant derivative of the normal vector. Now, what is this KAB? KAB is extrinsic curvature. And so what is extrinsic curvature, and what is the difference between intrinsic curvature and extrinsic curvature? These things we'll talk about in our next class on Wednesday. Okay. So I'll stop here for now with so what we know is that we will have some sort of Hamiltonian for general relativity, and that and that Hamiltonian will be, this should be H, sorry, it will be some function of the metric, 3 metric on a spatial slice, sorry, and the extrinsic curvature. This is not very good. Next time I'll use a slightly different app which has an eraser and everything. This time I was using slides, so let me write it down properly. H Hamiltonian. Okay. This will be our Hamiltonian. And then in the next class we will go over all of these. There are a lot of details, such as why is this expression true? Why is the extrinsic curvature to be identified with the covariant derivative of this? And why is that related to the Lie derivative? What is the Lie derivative, and so on and so forth. Okay. So I'll stop here because I think we have gone on long enough, and ask you for whatever questions that you have. From Nehal, so Nehal has a question, why not take x mu as the configuration variable? Okay, well, because x mu itself is a coordinate, right? And x mu, but the coordinate itself doesn't tell us anything about the geometry, right? So if I and a coordinate is not something that is invariant in any sense, right? I mean, I can perform a coordinate transformation. I can write my coordinates as something else. A point might have, so if I have a point in one frame of reference, it might have some coordinate values t, x, y, z. In some other frame of reference, it might have some other right? Welcome, Ilya. This ADM formulation is what people, which trips up a lot of people and scares them away from studying loop quantum gravity. So coming back to this, what Nihal was saying, that so the thing is that, okay, well, now you might say, right, so this doesn't really tell you anything about the geometry, right? What is geometry? Geometry is a measure of distances, for instance, right? It's a measure of areas and volumes, but the coordinates of a point don't tell you anything about the distance, right? So if you want to measure the distance of a curve, how do you measure the distance of a curve? You take the integral of this ds, right? What is ds? ds is the line element. Now, how do you write down the line element? Well, you write down the square of the line element using the metric, right? This is the basic notion, the most basic notion in differential geometry, right? And so it is this quantity which encodes the geometric information. So and of course, more fundamentally, because, well, when you look at this thing, the Einstein-Hilbert action, for instance, where is it? This Einstein-Hilbert action, this is a functional of, yes, I will answer that question in a second. This is a functional of the metric and the Christoffel connection, right? Now, the next question that Nihal is asking is that, well, HAB is also coordinate dependent. That's absolutely correct. It's coordinate dependent, but that coordinate dependence can be factored out at the end, right? So our quantities will be coordinate dependent, but at the end of the day, we will be left with something which is not coordinate dependent. We will be taking certain quantities which are, which turn out to be independent of the coordinates we choose. Yeah, Mustafa, please.
Oh, I had a different question. I had a different question though. You wrote down some terms that I don't fully understand. Those were SU2, SL2C. I think I know what SO3 means, but I don't understand the other.
Okay. Sure. I will explain what all of those are. Okay. I will explain what all of those are in our next class. So SU2 is the group of 2 by 2 unitary matrices. SL2C is the group of is a special linear group of 2 by 2 complex matrices. So it is also the same as the group of Lorentz transformations. It's something which is called the double cover of the group of. So maybe I will talk. I will have a session on all this group theoretic information. Okay, I won't take it for granted. And then Takato, you have a question. Is the dependence on the choice? So yeah, absolutely. So Takato is saying, am I saying your first name correctly?
Yeah.
Okay. So you're saying that, well, is the intrinsic metric, the 3 metric HAB, does that depend on the choice of the spatial surface? And it absolutely does, right? It does. So you can choose a different foliation, and then on that foliation, your metric, the 3 metric would be different, right? So this also leads to this issue, actually, that when you talk about the Hamiltonian formulation of general relativity, it is something which is a foliation dependent picture, right? So in some sense, a Hamiltonian picture breaks this general covariance, right? Because you're working with a certain with a choice of foliation. Whereas in full general relativity, you there is no such thing as a preferred foliation.
Does this foliation picture works with singularity?
So I mean, right. So again, so what one does when you, for instance, want to talk about spacetimes with singularities, right? You talk in terms. We generally use these diagrams known as Penrose diagrams. All right. So in terms of a Penrose diagram, we can talk about foliations even with spacetimes with singularities, yes. But then the question is, what happens at the singularity? At the singularity itself, of course, you can't define a foliation because, well, the singularity by definition is a place where, for instance, your curvature of spacetime is blowing up. Adel is asking, since this HAB evolves with time, is there a function that describes how it evolves with time? And there absolutely is, Adel. That function is this. That function is this extrinsic curvature, as I mentioned. Where is it? This extrinsic curvature, it's not showing up now. I'm trying to, when I show the annotation, because it's at the bottom. So it's the Lie derivative of this, as I was saying, right? It's this, if you look at this time derivative of the metric, right? This time derivative of the metric turns out that it is described by something called the extrinsic curvature. So this quantity at the bottom of the screen. And this extrinsic curvature we will talk about in our next class. What is it? It's a time derivative, but not exactly. It's something called the Lie derivative. And the extrinsic curvature also is a purely geometric property, by the way. So, okay. Any other questions? Now, of course, please, all of you, I request you all to join the Zulip chat group and post any questions that you have there. Let me quickly show you what Zulip looks like. Okay. So I will have to navigate away from the screen I'm sharing right now, and I will show you what Zulip looks like. So Nehal, you have a question. Is there anything apart from metric that can be used as a configuration variable? Sure, you can use different quantities. I mean, that's the whole point of, for instance, a canonical transformation on the phase space, right? And we will see later on that there is. But for the time being, let's first understand how to use the metric as a configuration variable, and then you can always go crazy with it. So this is what the Zulip window looks like. Right now the font is a little bit small. So for instance, on the right side here, you can see all the users who are signed up. Here is Nehal, then Takato is here, and other people are here. Mustafa, I don't see your name here, so you should also sign up for Zulip. So you can see in Zulip, for instance, now one of the problems is that the font size is very small, and I have to increase that. Okay, good. This is better, right? So you can see that on the left, you can see that there are streams. Okay. So you can see there's a stream general and stream literature. Now, when I click on general, it opens up and you can see there are these different subheadings. These are known as topics. Okay. So for instance, one topic is Zulip. Another topic is introductions. So if I look in introductions, this is general introductions. Now you can see, for instance, that here it is showing you that these posts were from December 4th and these posts below were from December 5th, right? So it allows you to follow the discussion on a very fine-grained level. And then, for instance, so here people are introducing themselves. So Victor is introducing himself, Torben, then Mohammed Bilal, then Devamalya, Nehal, Rajiv, Devadarshini, right? And so on and so forth. And then I'm also replying. And Takato has also introduced himself. So Zulip is really good. So if you're not on Zulip, please join Zulip and ask questions on Zulip. Okay. So the way you do it is you just create, so I'll make another stream. Anybody can make a stream, by the way. Anybody can make a stream and anybody can make topics in that stream. So let me say that I make a stream, ADM, okay? Everything about the ADM formulation, okay? Now it might turn out later that, well, this might be not such a good option for a stream. Maybe it's better to have ADM as a topic instead. So in that case, I'll rename this to something else. Can I rename it? I can't rename it, I think. So let me just trash this. And I'll make another, which is LQG. I'll just create that. So in LQG, then we can have a topic in LQG. So if I want to ask a question in here, I say new topic, LQG, and then ADM. Okay. And then I ask my question, blah, 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 whatever. And then the great thing is that I can write in LaTeX. So for instance, if I write HAB, then you can use this preview button. And if you use the preview button, you can see that it is being rendered as HAB nicely with all the indices. So if you're not using Zulip, please sign up for Zulip. I think most of you are. But okay. But please ask your questions on Zulip, so others can also see what you're thinking, and we can all learn from each other. Okay. All right. So with that being said, thank you all for coming, and I hope that I will see you all in the next lecture, which will be on Wednesday. Okay, 48 hours, approximately 46 hours from now. All right. So bye-bye, sayonara, and all that.
Bye-bye.
Thank you very much. Bye-bye. Bye.
Bye-bye, sir.
Thank you.